Welcome everyone to the second semester of 2021. Please check out the list of talks we have organized for you in the department's webpage. Today, it's a pleasure to introduce Carlos Eduardo Barbosa, also known as Cadu, as he signs his emails. Cadu has spent most of his academic life at the University of São Paulo, where he joined in 2005, graduating in physics, getting his master's and later the PhD. During his PhD between 2013 and 2014, he also spent some time at ESO in Munich, Germany. Since then, he has been a FAPESP postdoctoral fellow, both at USP IAG and at the Steward Observatory in Tucson, United States. Cadu works in the field of observational extragalactic astronomy, where he usually gets some data floating around and tries to make a scientific paper out of it, which is to say that he has been a kind of data scientist before the term became a trend. His words. His main interest is the measurement of the stellar population in galaxies, including their ages, metallicity, and elemental abundances. Thank you so much, Cadu, for accepting our invitation. You may start when you're ready.
Thank you, Anna. Thank you for the invitation for this talk. I'm really glad to talk about my work with you and share what I've been focused most of my last year of work in isolation. So it's good to talk to people about science again. Here I'm going to talk about the one galaxy that is pretty much the subject of my research in the last 80 years, NGC 3311. I'm going to talk about some interesting findings we get in collaboration with people from Europe, Chiara, Oxford, Magda, Lodon, Michael from ESO, and Tom from University of Concepcion. And the title here is going to be explained in detail, but the interesting finding that we got recently was that we found a surviving relic inside NGC 3311. We're going to talk about what this means and what we learned about the formation of Earth-type galaxies with that. So thank you for the invitation again. So let's get started. Starting from the broad picture in terms of what is being the subject of my research, I've been focused on different topics of galaxy formation and evolution, which is itself a large subject. And what has attracted me in the first place back in 2008, 2009, was actually how beautiful they look like. So this is one example of a large spiral galaxy. And if you go to Wikipedia, and that's what I do a lot of time, you just see what they mean, what they are, a simple definition. And here is a galaxy, simply a very large gravitationally bound system composed of stars and star remnants, gas, dust, and dark matter. So how do we get here? How we form these giant objects with billions of stars? Well, if you think about from the perspective of cosmology, at least when you look to the main cosmological model, the lambda CGM, which is the lambda cold dark matter cosmological model, we have a picture of how these galaxies form. This picture poses some important questions. First is that in the lambda CGM cosmological model, we start with a very homogeneous universe. So in this picture here on the left side, you see the universe at the beginning, and this is just dark matter. So we assume that dark matter is most of the matter of the universe. And we start with a very homogeneous, quite homogeneous with some fluctuations, and we evolve with time to form a cosmic web, which is large scale structure, where around 80% is dark matter, and you have 95% is dark matter and just 5% of ordinary matter, baryonic matter. So even though dark matter dominates the mass budget here, what we see is just the ordinary or baryonic matter. And the question for us that we can observe galaxies is how the baryonic component, how the regular matter forms the galaxies and large-scale structures that we see today. Here in this beautiful picture from the Lucid collaboration, you see on the left side the dark matter distribution, and on the right side the gas distribution. And here in the center is a node where we see a galaxy cluster, large galaxies, and we want to understand how this happens in the universe. When we look to galaxies here in the local universe, what we see is a variety of shapes, what we call morphology, and that they, most of the time in isolation, they look like spiral galaxies, disk galaxies with spiral arms. Sometimes they have bars, rings, and lots of features. And in some cases, you find more boring galaxies, the elliptical galaxies, the early type galaxies, which are more, they are not disks, they are triaxial, they are more amorphous. And usually they also are more massive than spiral galaxies. So my particular subject is concerned the most massive of those galaxies, which are the most massive Earth-type galaxies. And you can find those in the center of large galaxy clusters. Galaxy clusters are regions where you have hundreds, sometimes thousands of galaxies packed together in a relatively small volume. If you look to the very heart of these systems, you find the most extreme galaxies, at least here in the universe, in the local universe, which are usually the brightest galaxies in these clusters are known as brightest cluster galaxies. And in this picture here, this beautiful picture, you see one of these monster galaxies called NGC 1316, which is in the center of the Fornax cluster. And you can see this other galaxy here on top of which is a very large galaxy itself, but it pales in comparison to the large galaxy that we see in the center of the image. And these are pretty much the subject of my interest in my research. And the question that we pose regarding the formation of these large galaxies is mainly how they came to be, in the sense that where the stars were formed, were they formed there already? So was this a giant condensation of gas that became a monster galaxy, or it was formed by the gradual accretion of other galaxies that were kind of merging together, which is but then what's the balance between these two populations? For instance, we have galaxies formed there and others that came later. And how do you accrete these other galaxies on top to form these large galaxies? If you look to the universe at very high redshift, to use a very powerful telescope such as Hubble, and look galaxies to the universe when it was relatively younger, let's say redshift 2, or when the universe was like half of its age, you find it quite strikingly different universe. A lot of those massive, the most luminous galaxies at high redshift are relatively small. They are compact. So you find this population of galaxies, and here is one example of the first report of those galaxies, which are quite massive, though they have masses of 10 to the 11 solar masses. but they are relatively small with effective radius below one of the order of 1.5 kiloparsec. And those systems have been called the red nuggets. But when you look for, for instance, if you use the Sloan Digital Sky Survey to look for these galaxies, they are quite rare. Here in this example, you see some of the few galaxies that we found in a sample of more than 600 compact systems that are actually just very compact. So you see that there is an important evolution in the morphology and size and luminosity of galaxies over time. And what has been shown recently is that if you look to the sizes of galaxies as a function of redshift, so if you look back in time, the galaxies were relatively small. So this is, in the past, they were much smaller than they were on average here in the local universe at redshift 0. So for instance, the spheroid-like objects, which are the elliptical galaxies, they were around 5 times smaller when you measure their effective radius in the past than they are today. So what has happened to all those red nuggets from the past? And one proposed scenario is that they are simply the center of the local massive early type galaxies that we have in the universe today. So this population of red nuggets turns out to be just the center of very massive galaxies today, because they were already very massive in the past, and they just get bigger with time. So how this happened in practice? Well, in the last decade or so, there have been an emerging picture which seems to be well supported for massive early type galaxies, which is the two-phase scenario. So here in this picture, you see what to expect for one simple galaxy, how it evolves in size and also in color as a function of time. So in the past, you have lots of smaller systems merging together and form a large galaxy. And then over time, you only add more and more galaxies on top of that. But by the nature of this process, you have two different phases. Initially, you very quickly in the first 2 gigayears of the universe, you form the core, these red nuggets, for instance, in very fast and dissipative process, which means they are gas rich. And you form the bulk of the mass very early in the history of the universe. But then later, you will start to grow these galaxies over time by merging, both by major and minor mergers, but also new gas inflow, new gas that comes and forms new stars. But in particular, in the case of these massive type galaxies, what you see is that using simulations, for instance, in the second phase, they mostly grow by minor mergers. They can still suffer some major mergers, but most of the mass that is assembled over time in the second phase comes from minor mergers. And you end up making this galaxy looking larger, but because you were adding more stars in the surroundings of the core of the galaxy. So this is so you have a mass segregation between the stars that were formed there at the beginning, which are the in situ stars, and those that were accreted later, the ex situ stars. So this is an interesting simulation showing 3 galaxies. So on top you have a relatively smaller galaxy, 10 to the 10, and the second row 10 to the 11, the third 10 to 12 solar masses. And you see there how they evolve over time. So let's just pay attention in the example of the no, I'm sorry, no, over time. In the case of simulations, you know where the stars come from, so you can kind of take a picture of the galaxy and see which stars were formed there and which ones came later. And the case of massive L-type galaxies that you see on the bottom, you see that in situ stars dominate the very center region of the galaxy, but will make a much larger, more extended stellar halo around it. So it could be interesting to understand the in situ population in the local universe to understand how stars formed in the past. However, most of the galaxies pass through this extended phase where they accreted galaxies over time. And because this is the galaxy growth in the lambda CG universe is stochastic, some of these red nuggets may survive over up today without accreting other galaxies, but they are extremely rare. There are only a few examples in literature. I point out here there between these three papers there may be perhaps 5 galaxies known to be pretty much red nuggets in the local universe. So these are galaxies that survived up to this point without merging. But one interesting alternative that rarely explored before is to try to find this in situ population inside galaxies. And by the stochastic nature of this merging, even in the cases where galaxies have passed through the extended second phase with lots of minor and major mergers, in some cases, you still can keep surviving core in the center, which is pretty much the surviving relic of the red nugget inside this galaxy. So this fraction is very uncertain, but it's believed to be around 20% according to this paper. Oh, sorry. So, well, I've been working in this galaxy for a while, and it turns out it's a very nice candidate core, and this is NGC 3311. This is the brightest cluster galaxy of the Hydra cluster at a distance of 50 megaparsecs. You see how big it is in comparison to the other galaxies in the system. What's interesting about this galaxy is that if you measure the kinematic profile of the galaxy, which means you measure the temperature, kinematic temperature of stars in the system, it is lower in the very center part in relation to the outskirts. So this is, you can see in the upper right panel here in the center, the velocity dispersion is around 170 kilometers per second, whereas in the outskirts it has around 400 kilometers per second. And also from a previous work from by our group, we know that the central region also have a very different stellar population properties, which means the region in the very central region it looks like a very old system, metal rich, and the outskirts are relatively younger system and more metal poor. So but the problem before with this previous works is that we didn't have enough spatial resolution. We were using Poor's main version of an IFU observation, which is multi-slit observation. So we have a very low resolution in the center to actually understand better about the core of the galaxy. Well, that changed after a while when we got some data from MUSE. MUSE is an integral field spectrograph, large with wide field of view, very good resolution, and from the optical to the near infrared, and it's mounted in the very large telescope from ESO and the UT4 telescope, which is a sibling of the EQ1 that you see here in the picture. And this is on the right here. You see a picture of the MUSE instrument, which is quite scary. Well, I'm not going to details about the data. We got this data in queue mode, and it was produced by pipeline, which is a very complex task. So I'm going to jump to the more interesting part once we have the data. What was our strategy and what we get with that? So the first thing we did in this paper from 2018 was to try to understand what in terms of structures, different photometric and kinematic structures. So even though MUSE has a quite large field of view, it just encompasses just a small portion of the galaxy. So we have 3 pointings here along what is more or less the major axis here of the galaxy, another one that we use for the halo. And what we did in this to discuss, so these data cubes have around 90,000 spectra, but of course it's very hard to process the data because individually for each spectrum, because the synod noise is not good enough. So we used a very common strategy in this integral field observations, which is to use Voronoi binning, which means we combine the data of nearby spectra to make the synod noise larger at the cost of losing some of the resolution. So in the center, you have a still very good resolution because the synod noise there is quite good, but then in the outskirts, you lose synod noise because you are using larger and larger beams. But at least you have better, more usable data. In this first paper here, in this series, we use a synod noise of 70 just to get the kinematics. We get the kinematics of the system, which is the velocity dispersion, velocity, using very standard tools. In the case of this work, we use PPFX, so very basic stuff here. And what we get there as a result, we get maps of more detailed maps about the velocity and its higher order moments. So what you get here on this map is a map of the systemic velocity of the system. What is very clear is that the central region is slightly offset in relation to the outer halo. In the center, you can kind of see some tentative rotation pattern, but we made analysis with kinematry, and it seems like this system is not supported by rotation. It's just random motions here. So if you look to other, to the classification of the system, it's just a slow rotator with some interest, although the angular momentum races with radius, but I'm not going to talk about this in detail. And as I thought before, we knew this before, the velocity dispersion, which is kind of, if you can think about a kinematic temperature of stars, it's lower in the center than the outskirts, which means that the center here has a structure of, let's say, 100 kilometers per 108 kilometers per second structure, but the outskirts get hotter and hotter as a function of radiance. And this happens because this galaxy, this is not just we don't have just simple galaxy here. We have inner region, which is probably older and was formed in the past. And you have also lots of material that's coming, accreting around it, which were falling from all parts of the cluster, from the whole cluster. This is very close to the very center of the galaxy cluster. And this velocity dispersion profile, it rises and even reaches the velocity dispersion of the cluster itself, which is around 647 kilometers per second. We also measure other higher order moments, which are a little bit harder to interpret, but I'm going to talk about this a little bit more later. But this just talks about the shape of velocity, line of sight velocity distribution. So 83 is similar to the skewness of the distribution. H4 is the kurtosis. Well, then we have to look back to understand this galaxy in detail. We also use information from photometry, and we have access to deep imaging R-band from FORCE 2 from a previous paper, but we have to rework here on the photometric decomposition, because the previous version that we have in 2012 was not good for the very center of the galaxy. Now we are really focused on the very center of it. So we use GalFit-M to make the modeling of the central region. We model the three galaxies we see here. We use lots of different components in the form of Cersei components. And we use an interesting feature from GalFit-M, which is to use non-photometric components, which is a way to enforce that your residuals are mostly positive. And this is pretty much the result. So this is the original image on the left. And in the center, you have the model for the best model from GalFit. You see lots of gray areas here, which are just a mask. And here on C, you see the residuals. So we really made a good job of make a good description of the surface brightness profile of the galaxy. So this is an example, just one fake long slit, just to see how the model compares to the data. So in blue, you have the data from different spaxels, and the black line, you see the model that we produce. And in the case of 3311, which is the central galaxy, we needed 4 large one, offset by 8 kiloparsec, which indicates again that we have a composite system here, a galaxy in the center, and an extended halo. It's not even concentrical. Interestingly, we also found some tails related to probably to other galaxies that have been accreted over time. So just for an example here, this part that was masked here is HCC 26, one known dwarf galaxy. We found a very clear tail associated to that system. I'm not going to detail about what the details here. I hope you can take a look on the paper. But the idea was to here, we made a model to try to use the known photometric information to try to decompose the kinematics. And for that, we use what is called a finite mystery model. So just summary of the results is, well, for photometric, we have just 3 components, A, B, and C in our names. One is very compact, 1.5, 1.4 kiloparsecs, so let's pay attention to that. And when we make this decomposition, also in terms of kinematics, it suggests that both the 2 central regions have a very similar velocity dispersion. So we model them together. And it has a velocity of 150 kilometers per second, so it's even slower. It's just because we have more than one stellar component on the line of sight, it looks larger, 108, but it actually is smaller. And the main result of that paper are these models here you see on top. So these are the models for the 4 moments of the velocity distribution. and here is the residuals. So just inverted the order here of these slides. The idea here is if you look for the profile of the velocity dispersion, H2 and H4, you can find a quite good a description of all moments with this very simple model. So we just assume you have different components. Each has a single velocity and a different velocity distribution, pretty much like where each component is a isothermal sphere. And that kind of models find our data. One interesting part is that this kind of model doesn't require large anisotropies, which is a problem. You find lots of people claiming in the literature that these massive galaxies have large anisotropies that you see in H4, but it's hard to explain from theory, and this kind of explains this problem naturally. And we also get offset between the velocity and the CG halo for around 120 kilometers per second, which means that there's a bias of 30% between the velocity of the galaxy and the velocity of the cluster. Okay, so now going now for more recent work, we come back to this data because one of our goals was to study also cell populations, but that posed a much more difficult challenge. So in this case here, we take the same data we used before, but now restricting the study to the fields 1 and 2. And our goal was to simply measure cell population parameters, which is kind of standard H beta-list, alpha, and sodium abundances. But we also want to measure the initial mass function of this galaxy that we use using a bimodal parameterization. I'm gonna back to that point, because we want to also see whether this galaxy, NGC 3311, has a central bottom half IMF, which has been reported for other massive A-type galaxies. So 2 slides to explain pretty much what stellar mass function. It pretty much describes the distribution of masses of stars in a population. That's the idea. So the initial mass function is usually parameterized as in terms of power loss. So the number of stars in the range m and m plus gm, forget one part here, is given as m over with a power law alpha here. So here are some examples of different parameterizations for the initial mass function. The classic one is the Salpeter function, which is a simple power law, but more recent works have used double, triple power laws, or some kind of interpolated power laws, because what has been found is that in the Milky Way, this power law breaks down at lower masses, around and below 1 solar mass. So this is a very important and consequential aspect to understand the mass of galaxies, but it's very hard to measure in practice. So with the spectra in the optical and near-infrared regimes, we can measure the IMF using some lines in the spectra that are sensitive to the ratio between dwarf and giant stars. And the parameterization that we use in our work, the bimodal IMF, it's very common because we use the MUSE models. Is simply a power law at high masses with a different shape, and a taperate, which is kind of flat at low masses. That's pretty much similar to this Miller scala, but with a high-end changing. But actually, in practice, this because you also have a change in the normalization of the IMF, this impacts what we are measuring is pretty much the ratio between of stars with masses larger and smaller than 0.5, 0.6 solar masses. And the slope of the is a single slope. It's given by this parameter sigma b. So we get to great troubles to measure, to make this a nice modeling of these cell populations, because to measure all the parameters that we want, we end up with a set of 27,000 fixed cell population models. It's Emilis plus some sodium abundances that we use it combined with response functions. So this is, if people are familiar with template fitting, knows that using this number of templates is quite impossible in practice. And what I've been working parallel to all of this is to developing a code to study cell populations in general, which are called Paintbox, which is able to use different, it's kind of, I try to combine the features of different codes in a Bayesian, thinking about Bayesian methods. And with this, I was able to use a single cell population approach, but with a very complex model with 75 free parameters. And I have to use Bayesian methods. It's a very computely intensive process, but we got very nice fitting. So in this picture here, you see the best and the worst example. So you have residuals about of 1% in the over the whole spectrum in the center, and around 2.6 in the worst case here, and the average is around 1.4. So we get very good cell population measurements. And what we see now in the center is what we were expecting. In the center, we have a much older system than the outskirts. It's slightly more meta-rich, although the gradient is not very strong, but it's more meta-rich. But it's alpha poor in relation to the outskirts, which is interesting. And also, and here you see the bottom up here, you see it's also bottom heavy, but it becomes, which means the IMF becomes, or the slope becomes higher in the center than the outskirts. So we reproduce again this result for the velocity dispersion, and we also have the sodium, which is pretty much just, for our purposes here, is just a kind of contamination. We are interested in the IMF. So the results from this work, I hope you can take a look at the paper here. Is on archive already. We are waiting for the acceptance now after reviewing. The center region seems to be what we call surviving compact progenitor. In the definition of this paper, Pulson et al., which is based on simulations, because the light within 2 kiloparsecs is completely dominated by this old stellar population. In this case, in this very core that we found in photometry, and now we confirmed with stellar populations, and this galaxy is small velocity dispersion. I put 108, but it's actually probably 150 kilometers per second. Very old. Stars on average have 10, 11 gigayears old. Meta-rich, sodium-rich, bottom heavy IMF, 2.4 in the center of the slope. And then in the outskirts, and you see here in the figure, all the profiles. You have a profile for the age, this is decreasing, metallicity is decreasing, the alpha is increasing, sodium decreasing, and you see the IMF here. The slope is kind of constant in the center, but then decreases, and the sigma only increases. And all the parameters here that we can take a look at the paper, but the last one, the mismatch parameter and the surface stellar surface density. So it seems like we get this central progenitor here. Now, what we can learn about it, and this is from another paper we get as a result, a letter we get published recently, about understanding what's driving the variation of the initial mass function of A-type galaxies. So there have been several discussions in literature trying to put one physical aspect of the galaxy as the driver of the IMF. And the first one that was proposed was the velocity dispersion. So people say, so the galaxies with large velocity dispersion, which means larger mass, also have larger, more bottom-heavy IMF. And this is pretty much what this work here from Labra shows here. But these were pretty much for the center of the galaxies. More recent people have been doing especially resolved observations. For example, here in the Paddock paper, you see the center of galaxies. These are stacks of galaxies. It kind of follows the same trend. In the center is more bottom half. This is for SARSI M87 Virgo, the same thing. But here for our galaxy, we see a completely different pattern. It breaks down completely. It's the opposite direction. In the center, yes, it's bottom heavy, but in the outskirts, it's bottom light, but the velocity dispersion is much larger. So this is pretty much shows that the IMF in general, the velocity dispersion in general cannot be a good explanation for the variation of the IMF. This is, of course, expected. This is an extreme system, so far so good. There are other claims about the variation of IMF with the metallicity, in particular this paper from Martin Navarro, that found a very strong relation between the IMF and the metallicity. But this is a problematic from theoretical perspective. It's hard to explain if this happens. There are a lot of other problems arising in theory. So we found similar results. So our data point here shows similar results from all other papers literature. But we made a complex the analysis of the posterior of this modeling, and we note that there's actually a lot of this trend explained by the degeneracy between the two parameters in the parameter space. So changes in metallicity and IMF are correlated in the posterior distribution. So this is not a causal relation, it's just a degeneracy. So this is one explanation for this problem. And when you convert this parameter here to the mass to light ratio, this relation pretty much vanishes. Well, other properties still can be correlating well with the IMF. The distance to the center of the galaxy. So the center part of the galaxy is more bottom heavy than the outskirts. The aging, so it's more bottom heavy in the older populations, and also in stellar density. So the IMF is always dwarf rich in the center part of the galaxies, exactly where we have the surviving progenitor leaves. And this indicates, this is a conclusion of this paper, that the IMF, bottom heavy IMF, are driven by different conditions of stellar formation in the universe in the past, when the universe was very young. And this is a different condition that we have more recently in spiral galaxies and other systems. So I'm pretty much on time here. Okay, thank you very much for your time.
Thank you very much, Kadu, for your talk. For the people following us on YouTube, please write your comments in the chat box there, and our speaker will try to answer them later.